Greetings, my name is Angel Emilio Togutoran, and I will be presenting my machine problem in numerical methods. So, here is my code. So, to start, we're gonna enter a choice, which is number 1, and it's all about the bisection method. So, enter 1. And then we'll enter our function, which I compile in our user manual. So just copy paste the function from there, and then we're gonna enter our lower and upper bound, which are 4 and 5, and our tolerances, which is 0.0001, and we're gonna also enter our maximum number of iteration, which will be depends on the user. So I'm gonna enter 50 since that's my desired number. So in the right side of the screen, we can see the iteration table, and by analyzing it, you can see that the iterations stop at 15, and our approximate root is 4.30692, and at the lower part of the approximate root is our graph, and here the red dot here symbolizes the root, approximate root na nakuha na to from that function. So next is the key number 2, which is about the regular falsing method, where after entering the number 2, we will be greeted again by the program asking for a function, which we will enter the same function from before, and also the same lower and upper bound, and also tolerance. So the right side again, the iteration table stop at the iteration 8, and our approximate root is 4.30691, and below it is the graph for the regular falsing, and the red dot here again symbolizes the approximate root from the function. You can also solve for a transcendental function with the 1 and 2 key, or the bisection and regular falsing. So here I'm gonna take this function to try and solve it for the transcendental function example. Gonna try the bisection function method first. Enter our transcendental function, our lower and upper bound, which is 0 and 50. And the tolerance is 0.0000001 and maximum iteration of 50. So here you can see that the iterations stop at iteration 20 and our approximate root is 33.04400, and below it is our graph. As you can see, here is our approximate root pinned by the red dot. Next is our transcendental function sample for regular function. The same output, function again. And using the same lower and upper bound and also tolerance. So as you can see in the iteration table, iterations stop at number 21 and our approximate root is 33.04400, and below it is our graph for the regular Falso method. So the next topic will be the method of successive substitution, which is number 3 as for our choice. And then we're gonna enter our function. Our rearrange function to our initial guess, which is number 1, and our tolerance, which is 0.0001, and maximum number of iteration. So here is our iteration table. As you can see, the iterations stop at number 6 and the approximate root is 1.32470, and below it is our graph for this method. Next is second method, which is our fourth or number 4 in our choice. Again, we're gonna enter our function, which can be seen in our user manual. we're gonna enter our initial guess, which is 0, and our second initial guess, which is 0.5, and then our tolerance, which is 0.0001, and our maximum number of iteration, which is 50. As you can see in the table, iteration table, the iterations stop at number 16, and the approximate root calculated is 4.306913, and below it is our graph for the second method. The red dot is the approximate root for this method. Next is the Newton-Raphson, which is fifth in our choices. I'm going to enter our function. And our f prime x. And our initial guess, which is number 4, and tolerance, which is 0.201. So based from the iteration table, iteration stop at 4. And our approximate root is 4.306913. So below it is our graph for the Newton-Raphson method. Next is the Euler's method, which is number 6 in the choices. And then we're gonna enter our function, and then initial guess, which is -10, second initial guess, which is -5, third initial guess, which is 0, and our tolerance, which is 0.0000045. So in the iteration table, the iterations stop at number 5, and our approximate root is -3.15159, and below it is our graph for the Euler's method. Next is the Bairstow method, which is number 7. So our function, we're gonna enter our function, our coefficient of the polynomial, which can be unknown from the function, we've entered our initial guess for R and S, which is 0, and the tolerance, which is 0.0000752. So here we can see all roots from the function, and then below it is our graph for the Bearstein method. Next is Bears. Next is Gauss-Jacobi method, which is number 8. We're gonna enter our number of equations or unknown, which is 2, and then coefficient constant for row 1, and the coefficient for row 2. And then enter our maximum number of iteration, and also our tolerance, which is 0.000 0.00001. So here is our iteration table, and as you can see, the iteration stop at number 14, converge in, so the equation converge in 14th iteration, and here is our graph for that. Next is Gauss-Seidel, which is number 9. Again, we're gonna enter our equations of unknown, which is the same from before. Number 2. Coefficient for row 2. maximum iteration, and then tolerance. So based on the iteration table, the function converge in 8 iterations. So below it, we can see the graph for Gauss-Seidel convergence. So the blue one is for the x sub 1, and the red is the x sub 2. Next is the regression. So regression part is we can solve for our linear and quadratic equation. So enter our choice then. We're gonna choose if we're gonna solve for linear regression or quadratic regression. So we're gonna start with the linear regression, which is number 1. And then the program will now ask for the data points, which is we're gonna enter 5. One, two, two. 3, 5, 4, 5, 6. And then our value of x to evaluate, which is number 4, likely. So here's our table for our linear regression. So this is the x sub 2 and y sub 2. I mean x squared and y squared. So the mean of x is 3 and the mean of y is 4. And the a sub o is 1.30000, and our a sub 1, or the slope, is 0.90000, and the correlation coefficient r is 0.90000. So here's our graph for the linear regression. And then next, we're gonna try for the quadratic regression. Number of data points is 5. One, two, 5, 3, 6, 4, 10, 5, 15, and our x value to estimate y is 4. So here is the result. So the estimated y at x equals 4 is 10.05714, and below it is our quadratic regression graph. Next is the Lagrange interpolation polynomial, which is number 11 in our choice. So here, the program will ask again for the data points, which is 6, 5, 10, 15, 20, 25, 30, and then R1, 3.0062. And then y sub 3, y sub 4, y sub 5, and 6. And our value of x to interpolate is 12.5. So interpolated value of x is equals to 12.50000. Is s of x is equals to 9.17261. Below is our Lagrange interpolation graph. So the red dots are the data points. Next is the Newton divided difference interpolation, which is number 12 in the choices. Again, it's gonna ask for the data points, and we're gonna enter 7 for it, and 5, 10, 15, 20, 25, 25, 26, 41, 5. That's 3, 25.87, 625. And then 7, 6, and plus 3, and our x value to interpolate is 32.5. So here is a divided difference table. So the interpolated value of f, f 32.5 is equals to negative 5.7581. And below the interpolated value is our Newton divided difference interpolation graph. The red points are the data points for this function. And then next is the Simpson's 1/3 rule, which is number 13 in our choices. We're gonna enter function. Lower limit a is 0. The upper limit is 0.8. And n is 4. Here's the table. So the sum of f of x is equals to 24.35200, and the approximate integral I is equals to 1.62347. And here is our Simpson's 1/3 rule under area of the curve. Next is the Simpson's 3/8 rule, which is number 14 in the numerical methods of Manu. We're gonna enter our function, which is the same graph that we have, and also the same lower and upper limit. But n is 3. So here is the table. So the sum of f of x or weight times weight is equals to 11.70453, and the approximate integral I is equals to 1.17045. And here is our Simpson's 1/8 rule, area under the curve. Next is Rolle's rule, which is number 15 in the choices. And then we're gonna enter the same function again, and the same lower and upper limit. And the number of subintervals n is 1. here, sum of weight times f of x is equals to 184.56000. And the approximate integral I is equals 1.64053. And below it is our Moore's rule approximations. Next is numerical integration and differentiation, which is number 16 in our choices. So in this method, we only need the trapezoidal rule, so that's what we're gonna solve only for this method. Again, the same function as before, and the same lower and upper limit. Sub-interval, which is 4. Here is our trapezoidal low integration. So the approximation I is equals to 1.484800. And below it is our graph for this rule. And lastly is the Romberg integration, which is the last choice, or number 17 in our menu. So enter our function, which is the same as the previous one. Also the lower and upper limit, which is 0.0 and 0.8. So here's the Romberg integration table. So the final approximate integral using Romberg is equals to 1.64053, and below it is our graph for the function of x for the Romberg integration. And after trying all of that and checking each of the methods in this machine problem, we can now choose for 0, which is the exit of the program. So